Lesson 24, we're looking at hyperbolas this time around. Now, remember the hyperbola is specifically the set of points that's cut with a double cone. Now, I'm actually going to draw that picture so you can see how it's created. The hyperbola is set with, okay, there's a cone here, there's a cone here. And what I'm doing is I'm taking a plane that cuts through it this way, okay? And actually, so you'll see this thing here where that plane's cutting through, and this one here where that plane is cutting through. Okay, so that's where the hyperbola is coming from in terms of a physical representation. Now, the graphical or the geometric definition of a hyperbola is specifically the set of points in a plane that difference between whose distance from two fixed points, the foci, are a positive constant. Now, let me get this straight again. It's the set of all the points in the plane such that the difference between the distances from two fixed points, those foci, is a positive constant. So what I'm looking at here is this then. If I were to look at a hyperbola that sits like this, okay, and that's really what the hyperbolas generally look like, I'm going to have a foci here and a foci here. The distance from here to here minus the distance from here to here, okay, those distances subtracted from each other will be the same as the distances, let's say, from here to here, or even if we wanted to do that, from here to here. Okay, again, the distances subtracted from each other will be always a constant number. Now, how does this compare or differ? Question number 2. In terms of the ellipse, well, the ellipse has the addition of the values. The hyperbola is the subtraction of the two values. Now, what does the equation of ellipse look like again? It was x squared divided by a squared plus y squared divided by b squared is equal to 1. What do you think the hyperbola is going to look like? Again, what kind of equation do you think the hyperbola is going to have? Well, a subtraction sign. Okay. Now, there's a way that this will appear logical. Okay. Now, this what I drew right here is actually number 3. Okay. It's 3 pairs of those addition or subtraction lines, I should say. The real big question here is, how does this make any sense in terms of what it looks like? Well, we can take a look at the formulas like we did with the ellipse. That whole square root minus another square root all squared is equal to... It's not going to be pretty, and it's not really going to be worth the time. If you want to see it, you can ask me in class to work through it. That or I will not work through it later in the notes. I was taking a quick look. Now, let's talk about 4, 5, and 6. Now, we have specific new definitions that we have to play with. A transverse axis, a conjugate axis. Now, these are similar to the minor and the major axes in the ellipse. But the thing is with our graph looking like this, okay, where they are two separate pieces directing away or, again, around the foci, but away from each other, okay, then we have a new set of rules for those. So the transverse axis is specifically the shortest line segment between the separate pieces of the graph. Okay, and again, this is the best idea way to state it. I'm not sure exactly how they state it in the textbook or mathematically. But it is specifically, again, the shortest line segment between the separate pieces of the graph. So the transverse angle would be based on these points, and they would connect there. Okay, that would be my transverse axis. We also have a conjugate axis, and that's the line segment that passes through the center of the hyperbola and is perpendicular to the transverse axis. Well, that there is going to be like this. Okay, and it actually connects to two specific points. Those points actually being related to the value b here. Okay, just like the a corresponds to the major axis, the b corresponds to the minor axis in the ellipse. We have the a value corresponding to the transverse axis, and the b corresponding to the conjugate axis. Now let's see here. Let's talk about the vertices. The vertices of the hyperbola are the points where the hyperbola intersects with the transverse axis. Okay. Now notice we had to define the transverse axis before we could define where the vertices are. These points, okay, these points right here and right here are the vertices of our hyperbola. The problem with being able to define it this way is the fact that the transverse axis is only from here to here. Okay, and it's not necessarily always on the x-axis. If I shift this thing around, it's going to be somewhere else. So we can't just say that it's on the x-axis or it is the entire thing here. No, it is a specific length connecting the two what we would like to call vertices. So, with this being said, we could easily go through the idea of a hyperbola centered at the origin, okay, with a transverse axis based on the y-axis, a transverse axis based on the x-axis. Remembering again, the transverse axis is the one that connects the two pieces, not that it's part of the actual graph. Again, the actual graph would look something just like this, and that's it. That's what the graph would be for the hyperbola. It's drawn very, very terribly. But the transverse axis would be here. Let me actually draw this in red if I can find my red pen here. The transverse axis would be here. Okay. Your conjugate axis would be here. The vertices would be here and here. Sorry, the vertices would be here and here. The foci would be in here. Again, notice, again, the graph rotates around the foci. With all that being stated, that would be in terms of number 7. Okay, that would be in terms of number 7 on your notes. It's, again, the conjugate axis. This line here would be our transverse axis. These 2 points, this one over here and this one over here, would be our vertices. And this point here and this point here would be our foci. Everything else in this particular problem is basically unimportant. Okay, and we will actually come to the conclusion of all these details in the next video after we take a look at the generic formula for a hyperbola. Again, we're going to skip over that origin-centered one, and in the next video go straight towards the h comma k, because this will cover origin assuming h and k are both zeros. The equation for this will look very, very similar to that of a ellipse.